When you see a little robot vacuum gliding around your living room, quietly sucking up crumbs, dust, and pet hair, it seems almost magical. You press a button or schedule a cleaning, and the device does the job you used to bend and push a traditional vacuum for. But behind this convenience lies an intricate and fascinating factory process, a mix of robotics, precision engineering, supply chain logistics, and human labor. Today, we're going to peel back the curtain and take a full journey into how robot vacuum cleaners are actually made, from raw materials to the final product rolling off the assembly line. The journey begins far before the factory floor. It starts with design. Engineers and product developers spend months, sometimes years, designing the next model. They use CAD software to sketch every curve of the plastic housing, calculate suction pathways, test airflow simulations, and plan the placement of sensors. These aren't random choices. Every hole, every angle matters. The airflow system determines how efficiently the vacuum can suck dust through filters and into its bin. The wheel size determines how well it can climb over carpets and small thresholds. The sensor placement decides whether the vacuum avoids chair legs or constantly bumps into them. Even battery chemistry, weight distribution, and software algorithms are tested virtually long before any prototype exists. Once the design is locked in, the supply chain kicks into motion. The factory sources raw materials, ABS, and polycarbonate plastics for the casing, rubber compounds for wheels and bumpers, copper wire for motors, lithium-ion cells for the battery, silicon for sensors, and high-efficiency particulate air HEPA materials for filters. These components often come from different regions. Battery cells may come from South Korea, sensors from Taiwan, plastics from domestic injection molding suppliers, and microchips from global semiconductor manufacturers. All of them funnel into the robotic vacuum production plant, where the true assembly process begins. The first stage on the factory floor is plastic molding. Massive injection molding machines take in pellets of plastic, heat them to molten temperatures, and then inject the liquid into precision molds shaped like the top cover, dustbin, bumper ring, or wheel housing. Cooling systems solidify the shapes within seconds, and robotic arms eject the parts onto conveyor belts. Workers inspect these fresh parts for cracks, deformities, or color inconsistencies. If a flaw is found, the part is immediately recycled back into pellets, ensuring minimal waste. At this stage, thousands of identical black or white casings, glossy buttons, and protective bumpers are produced every day, stacked like puzzle pieces, ready for assembly. Meanwhile, in another part of the factory, motors are being built. A robot vacuum typically contains 2 to 3 different motors: the suction motor that powers the vacuum fan, the side brush motor that sweeps dirt toward the intake, and sometimes a drive motor for each wheel. Each motor begins with copper wire wound meticulously around small metal armatures. Automated winding machines spin these coils thousands of times in perfect patterns, then solder connections that allow electricity to flow. Once assembled, motors are tested for RPMs, torque, and noise levels. The suction motor in particular must balance high airflow with low sound, too loud, and customers complain, too weak, and the vacuum can't clean properly. At the same time, electronic control boards are produced. Printed circuit boards, PCBs, are fabricated in clean rooms, etched with copper pathways that allow electricity to travel between chips, resistors, and capacitors. Surface mount machines place hundreds of components per minute with pinpoint accuracy, guided by computer vision cameras that ensure no misalignment. These boards are the brains of the vacuum, hosting the microcontroller, memory chips, motor drivers, and wireless communication modules for Wi-Fi or Bluetooth. Once assembled, boards undergo a wave soldering process where molten solder washes across the underside, solidifying all connections instantly. Technicians test each board by plugging it into diagnostic rigs that simulate real-world conditions, checking if sensors respond, if motors spin correctly, if wireless signals transmit. Any board that fails is flagged for repair or recycling. The assembly line brings everything together. The process is almost like building a layered cake. Workers or robotic arms place the suction motor into the main housing, followed by the dustbin, side brushes, and wheels. The PCB slides into its slot, with ribbon cables and connectors linking it to sensors and motors. Ultrasonic sensors, infrared emitters, and sometimes LiDAR modules are added to the top or front of the unit, carefully aligned so they scan rooms with precision. The bumpers are fitted around the edges with pressure-sensitive switches underneath, so that when the vacuum bumps into furniture, it knows to change direction. The lithium-ion battery pack is slotted in last, secured with protective casing to prevent puncture or overheating. Once assembled, each robot vacuum moves to quality control testing. This is one of the most fascinating parts of the process. The vacuum is placed in a simulation chamber, a mock living room complete with obstacles, carpets, tiles, and even artificial pet hair. Engineers watch as the unit drives around. Does it map the room properly? Does it return to the charging dock? Does it avoid falling down simulated stairs? Sensors measure its suction power in pascals, checking that the airflow matches design specifications. Noise chambers record decibel levels, ensuring the machine runs within consumer comfort. Even endurance tests are run. Robots vacuum continuously for hours or days, climbing over small bumps repeatedly to simulate months of consumer use. If a unit passes all these tests, it moves on to cosmetic finishing. Branding logos are laser etched onto the top cover, or glossy stickers are applied. Protective films cover screens or touch-sensitive buttons. Some models receive polishing to ensure the surface shines without scratches. Then the robots are paired with their charging docks, wrapped in protective foam, boxed with manuals, and sealed for shipping. Pallets of freshly made robot vacuums are loaded into trucks or shipping containers, bound for warehouses and ultimately for homes worldwide. But the process doesn't end there. Modern factories implement constant data feedback. Every test result, from suction strength to software response times, is logged into databases. Engineers analyze these data points to identify patterns. Maybe one motor supplier is producing slightly weaker motors, or one batch of batteries doesn't hold charge as long. This feedback loop improves the next production cycle, ensuring consistency across millions of units. It's important to note that while automation plays a huge role, human workers remain essential. Robots might handle injection molding, soldering, or heavy lifting, but humans do visual inspections, troubleshoot faulty boards, assemble delicate parts, and refine software. A misaligned sensor by even 1 millimeter can throw off navigation, and it often takes human intuition to catch those subtle issues. Beyond the factory process, there's also sustainability. Many companies now recycle defective units, shredding plastic for reuse, recovering metals from circuit boards, and safely processing lithium-ion batteries. Some even design vacuums with modularity in mind, so that consumers can replace brushes, filters, or batteries without discarding the whole machine. This reduces waste and extends the product's life cycle. When you finally unbox your robot vacuum, press start and watch it zip around, you're seeing the result of thousands of steps, raw materials mined and refined, parts shaped and tested, electronics soldered and inspected, and entire teams of people and machines working in harmony. It's a fusion of old-school assembly line principles and cutting-edge robotics. Machines building machines that will serve in your home. Think about it. A device the size of a pizza box contains dozens of precision sensors, multiple motors, intelligent software, and a rechargeable power source, all engineered to work seamlessly together. That kind of integration is only possible because of the factory processes developed over decades of trial, error, and innovation. From the quiet hum of copper wire being wound into motors to the final seal of a cardboard shipping box, every step is a small miracle of modern manufacturing. So next time your robot vacuum quietly cleans while you relax, remember the story of its birth, the roaring machines molding its body, the precision robots soldering its circuits, the engineers testing it against obstacles, and the workers carefully boxing it for your home. Behind that simple convenience lies an extraordinary world of engineering, labor, and technology. Proof that even the most ordinary household gadgets can have extraordinary journeys. What's also fascinating about robot vacuum production is how the technology has evolved to the point where factories now use artificial intelligence and machine learning not only in the vacuums themselves, but in the very assembly process. In some cutting-edge plants, robotic arms with machine vision don't just follow fixed routines, they learn and adapt. If a component is slightly off-center, the system self-corrects in real time. This means fewer errors, faster production, and more consistent quality for the end consumer. It's an incredible loop where AI builds the machines that will later run on AI in your living room. Software integration is another overlooked part of the process. Once the hardware is fully assembled, the robot vacuum is plugged into flashing stations. These stations install the firmware, the code that makes it smart. This software allows the vacuum to recognize walls, calculate the most efficient cleaning path, and even integrate with smart home systems like Alexa or Google Home. After flashing, every single robot is run through a connectivity test to make sure Wi-Fi and Bluetooth modules work correctly. Without this step, even the most powerful vacuum would be useless in today's connected homes. And here's something else. Durability testing often looks brutal. Engineers drop the vacuums from small heights to mimic falling off shelves, expose them to dust chambers filled with fine particles to check filter efficiency, and run wheels across simulated rocky terrain to see if they'll crack. Some tests even involve intentionally blocking the suction to see if thermal sensors trigger automatic shutoff. It's all done to guarantee that once the vacuum arrives at your door, it's ready to handle whatever your home throws at it. Another fascinating element of the robot vacuum cleaner production process lies in the supply chain orchestration behind the scenes. While the factory itself might be the most visible part of manufacturing, the truth is that months of coordination are required to ensure that every screw, motor, chip, and sensor arrives on time. A modern robot vacuum contains hundreds of individual parts, many of which come from different suppliers across multiple continents. For example, lithium-ion cells may be shipped in from South Korea or Japan, microchips from Taiwan, sensors from Germany, and plastics from local sources near the plant. This means manufacturers must operate with razor-sharp logistics, where even a single delay can disrupt an entire assembly line. To manage this, most companies rely on advanced ERP systems that track incoming shipments, inventory levels, and production schedules in real time. It's an invisible ballet of global trade, and the end result is that everything arrives just when the assembly line needs it, with minimal downtime. The logistics challenges extend even further when it comes to compliance and regulation. Batteries, for instance, batteries are considered hazardous materials when shipped internationally, requiring special packaging and documentation. Circuit boards must meet electromagnetic compatibility standards. Plastic casings must pass flammability tests. Global demand for robot vacuums has also turned production into a race against time. During peak shopping seasons like Black Friday or Chinese Singles Day, factories must ramp up production to meet massive spikes in orders. This requires flexible assembly lines that can scale up shifts, bring in additional workers, and adjust logistics pipelines. Some factories even run 24/7 during these periods, with parts constantly moving in, vacuums constantly moving out, and shipping containers lined up at loading docks. If you found this journey inside the world of robot vacuum production fascinating, don't forget to like this video, share it with friends who love tech, and subscribe to the channel for more deep dives into how the everyday machines around us are built. Hit the bell icon so you never miss the next exploration into the hidden world of factory processes.